Good day everyone. Before we start with the lecture material, I want to emphasize something that was discussed in the lecture today. We looked at two concepts and I just want to clarify the difference between the two. The one was the singlet and triplet state concept, and the other was spin-orbit coupling. Now, in a sense, these concepts are related to each other, but they focus on different types of angular momenta. If we talk about singlet and triplet states, remember we looked at the helium atom, and in the ground state, both electrons are in the 1s orbital, and the 2s orbital is the next available orbital, but it is empty in the ground state. Excitation can take place, so if we excite these electrons, two options are possible. So in exciting the atom to an excited state, one of the ground state electrons goes to the 2s orbital, which is the first available orbital, and the excited electron can either have its spin parallel to the ground state or to the electron in the 1s orbital, or it can have opposite spin, or we can talk about paired spin. This is known as the triplet state, that is known as the singlet state, and we talked about the energies of these. And we said this is as a result of spin correlation. So what we're talking about here are the spins or spin angular momentum of the electrons interacting. So we're just looking at the quantum number lowercase s, s1 and s2 of the two electrons. When we talk about spin-orbit coupling, we have up to this stage only looked at the one electron system. So if we have an atom, we have a nucleus, and we have one electron orbiting the nucleus. Now, as a result of the orbital motion, it has orbital angular momentum given by the orbital angular momentum quantum number L, and it also has spin angular momentum given by the quantum number S. And we looked at the total angular momentum as coupling L and S. So here we're coupling orbital and spin angular momentum. This is only for one electron, this is for more than one electron. We only couple spins. So singlet and triplet has to do with the coupling of spins for more than one electron. Spin-orbit coupling has to do, well, in the example that we've looked at, about the coupling of orbital angular momentum and spin angular momentum for one electron, but we'll also see later on that we can do it for more than one electron. So the two concepts differ in the type of angular momentum that interact. Okay, so at the end of the previous lecture, we talked about the spectrum of sodium or any alkali metal atom, and we explained using spin-orbit coupling why you see two different lines in the spectrum, and that is due to the splitting of the p orbital into a j equal to a half and a j equal to 3/2 level, and we said the s orbital is not split. So when you get emission from two different levels giving two different lines. And we said that the difference in wave number between those two lines in your spectrum, so if you have your spectrum in terms of wave number, that difference is 17 per centimeter. So we are going to use that information in an example next. So example 10.5 asks us to calculate a spin-orbit coupling constant, so that's the A, for the upper configuration of the sodium atom. So sodium is an alkali metal atom, and we've just looked at the sodium spectrum, and it is asking us for the constant A. Now in illustration 10.3, which we've just done previously in class, we found that the change in energy between the two levels, we actually calculated the energy of each of these. Is equal to that. Now if you want to go from energy to wave number, you have to divide by Hc. So if we want to write that as a change in wave number, you can just go and check that. Let's quickly look at that. So wave number is frequency divided by the speed of light. So that is true, and we know that is true. That is nu. So E is Hc nu. Nu bar, if we replace nu with that. So if we want to get that, it is just E divided by Hc. So going from delta E to delta nu bar, it's 3 over 2 HCA divided by Hc is 3 over 2A. And remember we said in the sodium spectrum that is equal to 17 per centimeter. And that gives us a value for A of equal to about 11.3 or 11.5. This is the answer that Atkins gives. So we were able to calculate the spin-orbit coupling constant just by looking at the spectrum. So looking at the difference in wave number in the spectrum and using the energy level difference, one can calculate the spin-orbit coupling constant for a specific system. Now we are moving to something called term symbols. And this is just a more descriptive way of labeling the split orbitals than what we've been doing up to now. So in a way one can see that as an abbreviated description of the effect of angular momentum on the electronic orbitals or electronic energy levels. Remember, we are describing the electronic energy levels in an atom. This is what this chapter is about. So up to now we've talked about the J equals 3 over 2 level, or the J equals a half level. We saw that you get splitting of orbitals into different levels. But there's a more elegant way of doing this, and that is what term symbols and selection rules are about. And this is quite an important section. So we are going to look at how to derive a term symbol. Now that is what a term symbol looks like. And at this stage I know it doesn't mean anything, but just look at what we have. We have some kind of superscript on the left side. Then we have an uppercase symbol, and then we have a subscript on the right. And I'm going to explain to you what each of these means and how you get these for a specific configuration. Now we know that we use lowercase letters to label orbitals. So we have a p orbital or a lowercase s orbital, etc. And we're going to see that we use uppercase letters like that to label the states. So this would be a p orbital. These would be the different states of the orbital. So the orbital is split into different states. So the term symbol gives us 3 pieces of information, and again this is not going to mean much at this stage, but if you want to come back to this afterwards, this is a summary. We have this letter, we have the superscript, which we call the multiplicity, and then we have the subscript, which is the total angular momentum, quantum number. But we're going to look at how to derive this. Okay, now, if we have a one electron system, we've already looked at this. We have an electron, it has orbital angular momentum L, it has spin angular momentum S, and the total angular momentum is L plus S or L minus S. This is for a one electron system. If we have a many electron system, things get a bit more complicated. So now we have an atom with a nucleus with more than one electron. That electron has a spin angular momentum and it has an orbital angular momentum. That one has a spin and maybe it has an orbital angular momentum in a different direction. Same for that one and same for that one. Now let's number these to make sure that we don't confuse them. If that's electron 1, electron 2, electron 3, and electron 4. And all of these couple. So each electron will couple with itself, the L and the S, but then they will also couple with each other. Each L will couple with the other L, each S will couple with the other S, so you can imagine that this gets quite complex to get what we call the total angular momentum. So the total angular momentum is given by the symbol J. Now this is the difference between a one electron system and a many electron system. When we talk about a one electron system, we use lowercase letters. When we are going to look at a many electron system, we're going to use uppercase letters. So J, uppercase, is the total angular momentum quantum number. In the same way, we are going to have uppercase S, which is the spin orbital angular momentum quantum number, or you can call it the total spin orbital angular momentum quantum number, which is the effect of the S's of all these electrons. So the coupling of all the S's in my atom. In the same way, we get uppercase L, which is the total orbital angular momentum quantum number, which in this atom, which would be the combined effect of all the L's, how they couple. And then by combining all of this, how the S's couple, the L's couple, and how they couple with each other, we get the total angular momentum as given by J. Okay, so remember, for a one electron system, lowercase. For a many electron system, it's much more complex, and we start to use uppercase letters. Uppercase S, total spin orbital angular momentum, the effect of all the individual spins, all the lowercase s's. L, the combined effect of all the lowercase l's. And J is the combined effect of all of this, the combined angular momentum being the total angular momentum quantum number. So this is given in your notes in this text. The total orbital angular momentum quantum number L. There you have the magnitude, the number of orientations, and the number of values. And this is just exactly the same as we had for orbital angular momentum. So total orbital angular momentum and orbital angular momentum behaves in the same way. The same goes for S and lowercase s, and then we have J, the total angular momentum quantum number. So it behaves the same as J for a one electron system, and this is a many electron system. Now, how do we find these values? Firstly, let's look at finding the total orbital angular momentum. so uppercase L. Well, basically, you couple all the individual angular momenta, so all the lowercase L's. And the way that you do it is by using something called a Clebsch-Gordon series. So let's say you have a 2-electron system. There's your atom, you have electron 1 with orbital angular momentum L1 and electron 2 with orbital momentum L2. What you do to get uppercase L, and I always do it the following way. I get a maximum value by adding L1 and L2. And I get a minimum value by subtracting the two. And then you basically have all the integer values in between. So the Clebsch-Gordon series is L1 plus L2, L1 plus L2 minus 1, minus 2, minus 3, until you reach L1 minus L2, but we take the absolute value of that to ensure that it's positive. So that's described there. And there are also intermediate values. As explained here, using a vector representation. So for L2 and L1 equal to 2 and L2 equal to 1, for example, they can either work in the same direction or in opposite directions, but there's also an in-between value. So this will give you an L equal to 3, a total angular momentum of 3, total angular momentum of 1, so maximum, minimum, and then we have an in-between value. And you get this using the Clebsch-Gordon series. So let's look at this example and see if we can get these values using the Clebsch-Gordon series. So let's say L1 is equal to 2, so that is a d electron, and L2 is equal to 1, so that is a p electron. So how does an electron in a d orbital and an electron in a p orbital interact? So our maximum of our Clebsch-Gordon series is 2 plus 1, which is 3. The minimum is 2 minus 1, or 1 minus 2, it doesn't matter, is 1. And then you use all the values in between. So total orbital angular momentum L is the maximum, the minimum, and the value in between, as indicated here with vector notation. And that is how you get the possible values for total orbital angular momentum. So these are the total orbital angular momentum quantum numbers for this configuration. Okay, let's look at another example. For 2p electrons, L1 is 1, L2 is also 1, because they're both 2p electrons. So our total orbital angular momentum is L1 plus L2, L1 plus L2 minus 1, up to L1 minus L2. Maximum 1 plus 1 is 2, minimum 1 minus 1 is 0, and the value in between is 1. So my L values 2, 1, and 0. Now once you have the L values, you can get the symbol. Remember that letter that we need for the term symbol. And this is exactly the same as for the orbitals. If L is 0, your term is, or your symbol is S. If L is 1, it's a P, 2, it's a D, etc. So this is just uppercase letters, not lowercase. So for a 2, that would mean a D term. For a 1, it would be a P term. And for a 0, it would be a S term. Okay, so now we already know how to get the symbol for the term symbol. And these different terms, so your DP and S terms, have different energies because of the different orientations of the electrons' orbital and spin angular momenta. So they can have different orientations, some are up, some are down. So in a D term, your atom will have that one may be up, in an S term that one may be down, so they will have different energies. Now, very importantly, if you have a closed shell, the orbital angular momentum is 0 because they cancel. So we only look at unfilled shells when we determine term symbols, and this makes things much easier. So we only look at unpaired electrons. And then another important thing to remember, if you have a single electron, so now we're back to a one electron system. In that case, the value of uppercase L, so the total orbital angular momentum, is the same as the orbital angular momentum of that electron. So that is also a trick that you can use to make things easier. So let's look at another example, example 10.6, deriving the total orbital angular momentum of a configuration. Find the terms. Now basically the terms asks us for the symbols, S, P, D, etc., for the following configurations. So the first configuration is D2. So we have two D electrons. So for our first D electron, the orbital angular momentum is 2 for a D electron, because L is 2 for a D electron. And for the second one, it's the same. So use the Clebsch-Gordon series to find the total orbital angular momentum. Maximum 2 plus 2 is 4, minimum 2 minus 2 is 0, and we use everything else in between. So what terms would this give us? That would be a G term, F, D, B, and S. So you can see the effect that this coupling has on the orbital. So just by looking at the coupling between the orbital angular momentum, we already get splitting into 5 different options. And we haven't even considered the spin, the splitting of the spins. So this is not even the full story yet. And let's look at the second example, which is a p orbital. But now things get even more complex because we've got 3 electrons. So L1 for a p orbital is 1, L2 is 1, and L3 is 1. Now what do we do now? Because our Clebsch-Gordon series only allows us to couple 2 orbital angular momenta, not a third one. So what our trick is that we first couple L1 and L2, and then we call that result uppercase L prime. And then we couple uppercase L prime with L3 to get L. So let's begin by coupling the first 2 electrons, L1 and L2, to give L prime. So L1 is 1, L2 is 1, so our maximum value is 2, minimum is 0, so L prime would be 2, 0, or 2, 1, 0. And now we couple L3 is 1 with L prime equal to 2. So our maximum would be 2 plus 1 is 3, minimum 2 minus 1 is 1. So we have 3, 2, 1. We also couple L3 equal to 1 with L prime equal to 1 with that one. Maximum is 2, minimum is 0, and the in-between value is 1. and we couple L3 equal to 1 with L prime equal to 0. So L would be maximum 1 plus 0 is 1, and minimum 1 minus 0 is also 1. So the L terms that we have are 3, there are 2 2's, and there are 3 1's, and there's 1 0. So with 3 p electrons, you get splitting into 1, 2, 3, 4, 5, 6, 7, just by considering the orbital angular momentum. We haven't considered the spins yet. Okay, so that explains how to get the symbol in the term symbol. Now remember, if you have the symbol, for example P, the superscript on the top left corner, we call the multiplicity. And that is basically equal to 2 times uppercase S plus 1, where uppercase S is the total spin angular momentum, which you get by coupling all the lowercase s's, S1, S2, S3, depending on how many you have. And you do that in exactly the same way. You use a Clebsch-Gordon series. So uppercase S is S1 plus S2, S1 plus S2 minus 1, and your minimum is S1 minus S2. And that gives us the values of uppercase S. So there's nothing funny there. Now remember, for an electron, lowercase s is always equal to a half. So if you have 2 electrons, uppercase S is a half plus a half, or a half minus a half. So for 2 electrons, you always get a value of 1 or 0 for the total spin angular momentum. And it's illustrated here. So either you have the spins in opposite directions, giving you a total spin of 0, total spin orbital angular momentum of 0, or you have them in the same direction, giving you a total spin orbital angular momentum of 1. If there are 3 electrons, we first couple the first two spins, and then we couple the third, and then you get a total spin angular momentum of 3 over 2, or a half. So this I want you to go and check and confirm that you agree with that. We've done similar example for orbital angular momentum. This is just for spin angular momentum. So once you have uppercase S, you can get multiplicity, which is this just 2 times uppercase S plus 1. And that is what you put as a superscript on the left hand side of the symbol. So the multiplicity of a term is the value 2s plus 1, which you write there. So when S is 0, so for a closed shell like that, all the electrons are paired, so there's no net spin, and 2 times S plus 1 is 2 times 0 plus 1 is equal to 1. So you put a 1 next to the symbol. If you have a single electron, for example S1, in this case, remember we said for L, your L is equal to L, and the same is true for S. So in this case, uppercase S is equal to a lowercase s, which is always equal to a half. So 2 times a half plus 1 is equal to 2. So you put a 2 next to your symbol, like a 2s or a 2p. When there are 2 unpaired electrons, ladies and gentlemen, please make that correction. That should be uppercase S in your notes. Is 1 and then 2 times 1 plus 1 is 3, giving you a triplet. So you put a 3 next to the symbol. And we've talked about triplets and singlets before. So this is a singlet if it's a 1, a triplet if it's a 2, a doublet, triplet if it's a 3, and that's a doublet. We've talked about the energies of singlets and triplets, and we're not going to go into more detail. And the reason why the energies differ is because of this spin correlation, or the orbit. No, sorry, ladies and gentlemen, yeah, this is important. We talk about spin correlation. We're talking about spins here, how S1 and S2 interact. We're not talking about L1 and L2. So the singlet and the triplet terms differ in energies because of the way the spins interact. And here we're talking about a many electron system. Remember, to have singlets and triplets we need more than one electron. This is what we said. Okay, now there's one more thing that we need to write the term symbol. We know how to get the symbol, the letter, we know how to get the multiplicity, and then the subscript on the right hand side of the symbol is the total angular momentum, given by the total angular momentum quantum number uppercase J. And that is basically the combined effect of the spin orbital angular momentum quantum number, or spin orbital angular momentum, and the orbital angular momentum quantum number. No, sorry, let me repeat that. The combined effect of the spin orbital angular momentum and spin angular momentum, sorry ladies and gentlemen, spin angular momentum and the orbital angular momentum. So S and L gives you J. We have uppercase S, we have uppercase L, so now we can get J. Now we do this differently for single electron atoms, or many electron atoms, or several electron atoms. We've talked about the single electron case already. J is L plus S or L minus S, and in a single case, lowercase j is equal to uppercase J for one electron. So that's simple, nothing strange there, and we can now get the symbol, the full symbol. If you have more than one electron, so the many electron system, we now have to couple all the spins, so all the S's and all the L's. But the combination of all the S's gives us the total spin angular momentum. The combination of all the L's gives us the total orbital angular momentum. So by coupling those two, we can get the total angular momentum quantum number. So now we don't define it as spin or orbital, we just say total angular momentum. So this is quite easy to do because we just do this in another Krebs-Gordon series. We have L, uppercase L, we have uppercase S. So J is just L plus S minus 1 until you reach L minus S. And that gives you the total angular momentum. So let's go back to an example that we have looked at before. If we have this configuration, 2 p electrons, so L1 would be 1, L2 would be 1, S1 would be a half, S2 would be a half, so you can get L and you can get S. In this case, we are looking at the specific example where we consider only one combination of L and S. So if you look at the combination of L's, you will find that L is equal to 2, 1, 0. S is equal to 1 or 0. But let's just look at the combination of L equal to 2 and S equal to 1, because that will give you a multiplicity of 3, so that will give you your D3 term. Why? Because L is 2, give you a D symbol. 2 times 1 plus 1 is 3, so we're only looking at that combination. So if we want to determine the values for J, L plus S minus 1 up to L minus S. So for L2 and S1, 2 plus 1 is 3, 2 minus 1 is 1, and the value in between is 2. So for that term with a multiplicity of 3, we get the splitting like that. And this is the full term symbol. So things can get very complicated because we haven't considered the combination of L equal to 2 with 0, or 1 with 1 or 0, or 0 with 1 or 0. So that will give even further splitting, but we will have a look at an example shortly. Now there are some checks and balances that you can do or have in place to make sure that your answers are sensible. When L is larger than S, L is larger than S, the multiplicity is equal to the number of levels. The multiplicity, which is 3, is equal to the number of levels, which is 3. So you can always check that it makes sense. You can go and do this check. If you have a 2p term, you expect 2 levels, because in this case L is larger than S. Like we've just seen for this term, we have 3 levels because L is larger than S. However, when L is smaller than S, this is not the case, because in this case you will only have 1 level. So go and check that for that term, there's only 1 level. So now we're going to look at an example that basically covers everything that we have learned about term symbols. And I'm giving you a bit of a recipe on how to derive a term symbol. So the question is, write the term symbols arising from the ground state configuration of sodium, and then we look at an excited configuration of carbon. So let me first give you the method, just to summarize what we've said. Firstly, we write the electronic configuration, and remember we can ignore the closed shell. Step 2, couple the orbital angular momenta, which are all the L's, lowercase L's, to find uppercase L, which is the total orbital angular momentum. Third step, couple the spins, so the S's, to find uppercase S, which is the total spin angular momentum. Step 3, couple L, uppercase L and uppercase S, to find J, which is the total angular momentum. And all of this you do using the Clebsch-Gordan series, steps 2 to 4. And then you express the term as a symbol that you get from using L, the letter. 2s plus 1 is your multiplicity, and there you put the value of J. So where that is the appropriate letter in uppercase. So if you follow this recipe, you can basically determine any term symbol. So let's look at the first example, sodium. We want the term symbol for sodium. First step, write the electronic configuration. We only consider we don't consider the closed shell electron, so we only consider the single 3s electron. For that electron, L is equal to 0, and we said for a single case that is also equal to uppercase L, because there's only one electron. Then we couple the spins for that one electron. That is also the case. Because there's only one electron. So J in this case is equal to J, L plus a half, which is the same as L minus a half in this case. 0 plus a half is equal to 0 minus a half, stays a half. Multiplicity is 2 times S plus 1 is equal to 2. So our symbol, because L is 0, the symbol is an S, uppercase S. Multiplicity is 2 and J is a half. There we have the term symbol for the ground state of sodium. And we see there's only one term, so there's no splitting, which is exactly what we've said for the sodium atom, for the ground state specifically. Okay, now let's have a look at the second question, the B part. Now things get a bit more complex. We are talking about the excited configuration of carbon. There we have the electronic configuration. Now remember, we don't consider the closed shell electrons. So what we're going to look at are those two electrons. There's one p electron in the 2p orbital and 1p electron in the 3p orbital. So it's a 2 electron problem. L1 is 1, L2 is 1, S1 is 1, sorry, S1 is a half, S2 is a half. So firstly, couple orbital angular momenta. Clebsch-Gordon series, L1 plus L2, L1 plus L2 minus 1, L1 minus L2, 2, 1, 0. Couple spins to find S, S1 plus S2, S1 plus S2 minus 1, S1 minus S2. Half plus a half is 1, half minus a half is 0. So remember we said for 2 electrons, your total spin angular momentum is always 1 or 0. Let's get the multiplicity. So in the S equal to 1 case, the multiplicity is 3. In the S equal to 0 case, the multiplicity is equal to 1. Okay, so what do we have here? We have 3 different values of L, 2 different values of S. So the fourth step would be to find J. Now in order to do that, you have to couple each of these with each of these. So now things get complicated. So now you have to keep your bearings. So we have L equal to 2, L equal to 1, L equal to 0. That gives us a D term, a P term, and an S term. But remember, we have a spin equal to 1 scenario, and we have a spin equal to 0 scenario. So the multiplicity for the spin equal to 1 scenario we said is 3. The multiplicity for the spin equal to 0 scenario is 1. So this is what we're dealing with. So now we have to couple all of these. So let's start with that term, the 3D term. For that term, L is 2, S is 1. So J is maximum 3, minimum 1, and there's a 2 in between. So the terms that you will get, 3, 2, 1. Let's now move to the 3P term. L is 1, S is 1, so J is 2, 1, 0. So we have a 3P, 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 2, 1, 0. Let's look at the 3S term. L is 0, S is 1. So in this case, J is L plus S, which is 1, L minus S, which remains 1. So it's 3S, and J is just 1. Sorry, P. No, sorry, 3S, yes, that's right. 3S1. Okay, now we still have this row of terms to look at, 1D, 1P, and 1S. Let's start by looking at the 1D term. Let's just keep that there. So the 1D term, L is 2, S is 0, J is just 2, so you have a 1D, 2 term. Then we do have the 1P term there. L is 1, S is 0, so J is 1. It will give us a 1P, 1 term. And the 1S term, L is 0, S is 0, so it will give us a 1S, 0 term. So in this case we don't get splitting for any of these. However, we do get splitting for these ones. And let's just check. Remember we said when L is larger than S, the multiplicity equals the number of terms. So that is true in this case. So there we have the term symbols for this excited state of carbon given by that configuration. So you can see even if you only have 2 p electrons, because you have 2 electrons and their spins and the spin orbital angular momentum I keep saying spin orbital angular momentum. Spin angular momentum and orbital angular momentum interact with each other. You get splitting into so many terms because of the different orientations of the angular momenta. And we can now derive the different term symbols, and each of these will have different energies. Okay, so now that we know how to write term symbols, we can use these term symbols to specify any state of an atom, and we also use it to give spectral transitions or to define a specific spectral transition. If we go back to our sodium case, remember we said we have a 3s orbital and a 3p orbital and we get splitting of the 3p orbital. And if you determine the term symbols for those two orbitals, and I want you to go and check that if you agree with that, and also for that one, you can now define the transitions in the sodium doublet using these term symbols. So an electron in the 3p1 orbital going from the 2p3/2 level, which would be that level, to that one, or starting from that one to that one. So by convention we give the upper level first with an arrow going to the lower level. So this is a more compact way of specifying which level we are talking about. And we can do the same thing for absorption, then the arrow is just in the opposite direction. So again, the higher one is given first. We have already talked about selection rules, and we have to conserve angular momentum, and the photon has an angular momentum of 1. So we can also express the selection rules in terms of term symbols, and we can express them in the following way, where the change in total spin angular momentum must be 0, change in total orbital angular momentum must be plus or minus 1, change in angular momentum must be plus or minus 1. And this is normally the one that we use. So don't worry about the others too much. This is still the important one, because it gets very complex if you have to look at the total spin momentum, spin angular momentum, and total orbital angular momentum. So this is still the one that we are going to use. Just something finally about the energies of these terms. Typically the term with the highest value of S will lie lowest in energy, and then if they all have having the same value of S, the one with the highest L will have the lowest in energy, will lie the lowest in energy. So first look at S and then you look at L, and then the lowest J will also lie lowest in energy. So this is the one that we've been using up to now. The one with the energy level with the lowest J value lies lowest. So in this case they have the same S, but the one with the lowest J has the lowest energy. So this is how we order the energy levels, and that's what we normally look at, because we don't look at very complex systems. We normally look at J values to order the energy levels.